This is a run through the extraction of metals, which is part of AQA AS chemistry. And this is the first page of your core notes, and you'll see from this the two parts at the top, the idea of the principles of metal extraction. So these are the things that you'll see in your notes. And if you have a quick look through that, you'll see various things like the ores and how you extract using carbon, electrolysis, etc. So you'll see all of that in the core notes. But take a look at this part down here, because this is quite important. You'll see that there's quite a large bit where it talks about the environmental aspects of metal extraction. And you're going to see that, particularly when you come to the past paper questions, that there's quite a bit about the environmental aspects. So keep an eye out for that as we go through this. The first page after this is the principles of metal extraction. And this is quite important. First thing to note here, and you'll see again this come up quite a bit in the past paper questions, metals are extracted by reduction. Now, why should it be reduction? Well, most metals are found as compounds. So they're combined with things like chlorine, oxygen, etc., which means that they're going to have a positive oxidation number. Remember, metals generally lose electrons, so tend to therefore have a positive ion or positive oxidation number. When you're extracting the metal, what you're doing is you're turning them from having a positive oxidation number to an uncombined element, which has got an oxidation number of 0. So it's going from positive to 0. In other words, it's lowering its oxidation number, and that is reduction. Another way of looking at it is that the positive metal ion must have accepted electrons, and gain of electrons is reduction. So in all of this, metals are extracted by reduction. That's quite important. The second thing to say as well about metals is quite often we see them being extracted from their oxides, but how they occur in nature is quite often not as oxides at all, but as sulfides. And sulfides are quite easily converted to oxides, and how we do this is by roasting the ore in air, and air obviously contains oxygen. Now, the reaction is fairly straightforward. A metal oxide, so here the one illustrated, the zinc sulfide, is then reacted with oxygen and turns into the metal oxide, zinc oxide. The reaction is basically like a burning reaction. The zinc is combined with oxygen, but also then the sulfur combines with oxygen. So then we also get this gas given off, sulfur dioxide. Now, where have we seen this before? Well, if you think back to Unit 1, sulfur dioxide, if it's allowed to escape into the atmosphere, causes acid rain. So this is going to be one of the environmental aspects of it, that whenever this escapes off into the atmosphere, it can dissolve in rainwater and lead to acid rain. Some equations for this: so sulfur dioxide combines directly with water and gives us sulfurous acid, H2SO3, so that's one potential acid in acid rain. But also in the atmosphere, sulfur dioxide can be oxidized sulfur trioxide, SO3. So there's an equation, sulfur dioxide being oxidized into sulfur trioxide, and then the sulfur trioxide combines with water and gives us sulfuric acid, H2SO4. So acid rain is a mixture of those two acids, sulfurous and sulfuric acid. But this could potentially be a benefit to industry, because if it could be collected in a correct way, you could combine the sulfur dioxide with oxygen to make sulfur trioxide and then convert that into sulfuric acid. And sulfuric acid is a commodity, something that could be sold, and therefore industry could produce this. And therefore a waste product could end up as a profitable product. So there's an environmental problem with this. If we let it escape, sulfur dioxide goes into the atmosphere, leads to acid rain, but there is potential for making this a benefit by making sulfuric acid, which could be a profitable substance. The last part here of the principles is the reducing agents, and you'll see that first of all we've got 4 potential reducing agents, and we'll see these all in the core notes. And if you look at the 4 of them, there's the 4 things that we look at. So coke or carbon, and as we'll see shortly, this is quite a good substance if the metal is of moderate reactivity or low reactivity. Carbon's round about the middle of our reactivity series, you think back to GCSE, so it can steal away oxygen and therefore can reduce the metal oxides. Now, there are some metals, however, which could potentially be used. You could use carbon to extract them, but there is another problem. Some metals, rather than letting the oxygen extract, or letting the carbon extract the oxygen, what they do is they actually combine with the carbon. Now, the three examples are titanium, tungsten and aluminium. Now, if the right conditions were there, they potentially could be produced by carbon. However, under the conditions needed, high temperatures and so on, quite often what they do is they react with the carbon. So titanium would form titanium carbide, tungsten would form tungsten carbide, aluminium carbide. Now, those substances basically lead to the metal that's produced having little traces of this in it. The metal, therefore, is not as good as it should be. It's a bit less crystalline, and therefore the properties, the typical metallic properties, aren't just as good, and therefore the carbides interfere with this. So that's not used. So sometimes you'll see questions where it says, why, despite the fact that carbon could be used, is it not used? And quite often the reason is that the carbon forms the carbide, and the carbide basically leads to metal being less suitable than it should be. I will also see an example of using hydrogen, and the example that we normally use is one called tungsten. The metal is called tungsten. Now, this is a metal that you would have been more familiar with maybe 20 years ago, because metal bars that were used to heat up, so electrical heaters that had these metal bars that glowed, they had tungsten wire. Filament lights, which are now starting to be used less and less because they're basically not very energy efficient, so we're using LEDs and various other types of lights now. They used to have tungsten wire in the centre of it. So although tungsten is a metal that's quite good, it can be heated, it's not very reactive and so on, it gives out heat, gives out light, but it's not very efficient. So it is a metal that's probably at the moment decreasing in the amount of usage, but we'll see how we can use hydrogen to extract it. We can also extract metals higher up the reactivity series, and with those ones, what we would do is we'd use a metal that is itself extracted by, as we'll see shortly, electrolysis. And the example of this is titanium. Now, any of you that have used titanium or have got anything made of titanium will know that titanium is a very expensive metal, and we'll see as we go through it the processing and the fact that we're using a metal that's high up the reactivity series means that titanium is expensive. There's a lot of processing and expensive chemicals used for it. And then the final one, which we'll be familiar with from GCSE, is electrolysis. And we'll see examples of where we use things like electrolysis to extract metals like aluminium. And you'll see that quite often, or a lot of the information from that is very similar to what we had at GCSE. Okay. On to the first extraction, and the first extraction uses the idea of the reduction using carbon. Now, the example that we see at the top here is iron, and you may remember from GCSE that iron is extracted in the blast furnace. So, quick read over the top bits there, you'll see that the blast furnace is basically a large-scale extraction, so iron is relatively cheap because of the quantities that's used and so on. Also, it uses a substance that's not particularly expensive, because to extract it we basically use carbon monoxide, which we'll see shortly is generated from coke, which is a form of coal which has been heated. So, first thing is the ore, hematite, and hematite is basically iron oxide, and it's more specifically iron 3 oxide. So it's the same thing that appears in rust, that's a ready thing in rust. So formula Fe2O3, so iron 3 oxide is the form of iron. The reducing agent is carbon monoxide, and this basically can reduce the iron from the iron oxide because it's more reactive, and being gaseous, move up inside the blast furnace and extract it. There are a couple of things. The blast furnace, you may remember from GCSE, there's the three things fed in the top: carbon, which is in the form of coke, which is basically coal that's been roasted in the absence of air, and it's basically a form of carbon; limestone, which is calcium carbonate; and then what we've talked about there, the hematite iron oxide. Now, this basically fills up this section of the blast furnace, in fact the whole of the blast furnace there, so it's solid filled in. But at this part of the blast furnace, you'll see that hot air is being blasted in. So the carbon that's down here combines with the oxygen from the hot air, and it makes carbon dioxide. Now that's basically the same thing that happens in your barbecue whenever your charcoal burns. So that generates heat. So this part down here is the hottest part of the blast furnace. So you'll see the equation for that fairly simple. Carbon plus oxygen gives us carbon dioxide. There's a hot gas that's produced, carbon dioxide. It rises, bumps into more carbon, which is in here, obviously from the coke and so on. And then we get this second equation that shows it. Carbon dioxide reacts with carbon, and that gives us carbon monoxide, which again is a gas, and that continues to rise up the tower. So reduction really takes place somewhere around this zone with carbon monoxide, lots of carbon monoxide being produced. Now the main equation, and do your best to try and remember this one, is that it's the reduction of iron oxide. And if you look at the reaction, iron oxide to Fe2O3, carbon monoxide CO, that gives us iron and carbon dioxide. Now the reaction is reasonably easy to remember. If you remember CO going to CO2 and Fe2O3 going to Fe. The balancing sometimes takes a little bit of difficulty, so the way I try and get you to remember it is, look, there's 3 oxygens there. Each oxygen, or each carbon monoxide molecule, these molecules here, can take 1 oxygen, so therefore we need 3 of those to react with Fe2O3. So 3 COs take away those 3 oxygens and then become 3 CO2s. And if you remember that, you tend to get it balanced, and then you get a 2 in front of Fe. The other substance that can be reduced by carbon quite easily is copper. Now, copper is reduced from copper to oxide, and you can do that directly by heating with carbon. So the equation is fairly straightforward, copper oxide plus carbon, and then depending on the ratio, you can either get carbon monoxide or carbon dioxide. Let's go for maybe the slightly harder one to balance. Let's do carbon dioxide, CO2, and for that to happen, we need to have 2 oxygens there. So balance, we put 2 in front of the CuO and then a 2 in front of the Cu. And you can see that's simple reduction. Now that requires heat. But here's the environmental problem. Look, carbon dioxide is produced. Now what that does is it releases carbon dioxide to the atmosphere. And as we may remember from Unit 1, carbon dioxide levels appear to be rising, and that is linked to global warming. So look back in your Unit 1 notes and know a wee bit about that. You'll see that come up over and over again. This basically works best with ores that have got a high percentage of copper in them, or high grade ores. And you're going to see this shortly as well. The other way we can get copper is by taking copper carbonate, malachite, you may remember it, a green substance that we used back at GCSE. And what we can do is we can first of all roast it. CuCO3 could be heated, and it decomposes into copper oxide and carbon dioxide, and that's an equation that we're familiar with from GCSE. And then the copper oxide could be reduced, as we saw up there. The other way we could do it is by heating the copper carbonate directly, CuCO3, in carbon, and that'll give us copper plus carbon dioxide, CO2. And to balance that one, we've got 3 oxygens here, we've 2 there, so let's get 6 common multiple, 3 in front of the CO2, 2 in front of this, and then that would mean we need a 2 in front of our copper. And that's all balanced. We've got 3 carbons over there. Final substance that could be reduced with this is manganese, and ferromanganese is an alloy of iron and manganese, a high content of manganese. It's made by heating a mixture of the manganese dioxide and iron oxide with carbon in a blast furnace. So you can imagine that the iron oxide is reduced the way that we have up above. And the equation for the reduction of manganese 4 oxide, remember it would be MnO2, and that could react with carbon. And again, we can either get carbon monoxide or carbon dioxide. Let's make carbon monoxide this time. So therefore we would need 2 carbons to give us 2 COs, and the manganese is reduced.